Hello, welcome to the course SJPHY1 B01 Mechanics 1. The contents of this course is taken from An Introduction to Mechanics by Klepner and Kolenko. We will continue to discuss topics from Chapter 4, Work and Energy. In the last class, we have seen what is the potential energy function of a harmonic oscillator. We know that this is a second order function which corresponds to a parabola, and if the energy of this system is sufficiently small or less than zero, then the motion is bounded by two turning points. And at the equilibrium position, potential energy has a minimum point. And this is true for any bound system. So for any bound system, the potential energy has a minimum at the equilibrium position. That's why we call this equilibrium position as the stable equilibrium position. Now, if the total energy is low enough so that the motion is restricted to the region where the curve is nearly parabolic, then the bound system oscillates like a harmonic oscillator if it is slightly perturbed from its equilibrium position, right? So you take any bound system. So let's say this solid line represents the potential energy of a given bound system. And if the energy is sufficiently small, then you can see that near the equilibrium position in this region, this resembles a parabola, right? So in this small region, you can approximate your bound system to a harmonic oscillator. Why? Because in this small region alone, the potential energy function is parabolic, which is the nature of a harmonic oscillator. Now the question is, mathematically, can we prove this? Okay, so we can do that using Taylor series expansion. So according to Taylor theorem, any well-behaved function f of x can be expanded into an infinite series known as Taylor series. Okay. So we have a given point x. We don't know the value of the function at this given point. So what we are going to do is we will take a known point x naught, and the condition is that x naught should be very close to x. Okay. So if that condition is satisfied, then we can write the value of the function at the unknown point x in terms of value of the function at the known point x naught. So the Taylor series goes like this: f of x equal to f of x naught plus x minus x naught f prime x naught, where f prime is the first derivative. This is df by dx at x equal to x naught, plus half x minus x naught square f double prime x naught, where f double prime is the second derivative. Then you have 1 by 3 x minus x naught cube f triple prime x naught, etc. Okay. So this is true for any well-defined function. So if you take a bound system whose potential energy function is u of r, then we can expand u of r using Taylor series about the equilibrium position r naught. So you can write u of r equal to u of r naught plus r minus r naught du by dr at r naught plus half r minus r naught square d square u by dr square at r naught plus all the higher order terms. Now, if the displacement is sufficiently small, what is the value of displacement? R minus R naught, right? Because R naught is the equilibrium position, R is the instantaneous position. So R minus R naught gives you displacement from the equilibrium position. So if this value is sufficiently small, then you can neglect all the higher order terms beyond the second order. Now, why do I say like that? For example, assume that r minus r naught is very small, like 0.1. So in the second term, you have r minus r naught square, so which will give you 0.01. And in the third term, you will have 0.1 cube, which is 0.001. So you can see that 0.001, it's much smaller compared to the previous two terms, right? So when the value as such is very small, its higher order powers are going to be even smaller. So you can conveniently neglect all those terms when your displacement is sufficiently small. So we are going to terminate our infinite series at the second order. We can also do some more simplification, because we know that since this is a bound system, at the minimum point, at the equilibrium point, potential energy has a minimum. So at the minimum point, the slope is going to be 0. In other words, du by dr at r equal to r naught is going to be 0. So the second term vanishes. Now I can write u of r equal to u of r naught plus half r minus r naught square d square u by dr square at r naught. Now, if you compare this with the potential energy function of a harmonic oscillator, so this is the potential energy function of a harmonic oscillator, u of x equal to half kx square, and the function doesn't change if you add a constant to it, because u of x equal to half kx square is nothing but a parabola. When you add a constant to it, you are basically applying an offset. So you are shifting the entire parabola either upwards or downwards. In either ways, the shape of the parabola is not going to change, only the offset changes, right? So u of x equal to constant plus half kx square is perfectly valid for a harmonic oscillator. Now you can compare these two functions. So first one is the potential energy function of a bound system with small oscillations. Second one is the standard harmonic oscillator potential energy function. So here you have u of r naught. R naught is the equilibrium position. The corresponding value of the potential is a constant. So basically this is a constant. So first term is similar. Then you have half factor here. R minus R naught is the displacement from the equilibrium position. Here x is the displacement from the equilibrium position, because you consider equilibrium position to be 0 in this case, right? So this term is also common, and the only difference is here you have the spring constant k, and here you have a second order term. Since these two equations are comparable, you can say d square u by dr square at r equal to r naught is nothing but the effective spring constant k. So in summary, any bound system can be approximated to a harmonic oscillator if the amplitude of the oscillation is sufficiently small. Now, what are the implications of this approximation? For example, when you look at a molecular system, because in the previous class I have said, if you take two atoms which are tightly bound, this is nothing but a molecule, right? So you two atoms combine together, they lose some of the energy. As a result, they go to an equilibrium position and they form a stable molecule. Now let's assume that we have two atoms of masses m1 and m2 which are bound together in a molecule with energy so low that their separation is always close to the equilibrium value R0. So we know that this is the potential energy curve of a molecular system, and the energy, if the energy is very small, basically the two atoms are going to be confined to this small region, and in this region potential energy curve is parabolic, which means I can approximate this to a harmonic oscillator in this region. Right? So with the parabolic approximation, there's an effective spring constant k equal to d square u by dr square at r0. This also we know. Now the question is, can we find the vibrational frequency of the molecule? Now, why is the vibrational frequency is very important? Because once you know the vibrational frequency of a molecule, you can get a lot of information regarding the phase transitions in that molecule, or the bonding of the individual atoms of the molecule. You can also get some of the kinetics and mechanisms of the chemical reactions in which the molecule has taken part. So you can get a lot of information from the vibrational frequency. Now you can calculate the vibrational frequency mathematically using the harmonic oscillator approximation. Let's see how do we do that. Let's assume that the two atoms are connected by a spring of equilibrium length R0 and spring constant K, because we know that for small oscillation this molecular system behaves exactly like a harmonic oscillator or exactly like a spring system. So you have mass m1, m2. If there is no force acting on the system, the equilibrium distance is R0, and m1 is at a distance r1 from the origin and m2 is at a distance r2 from the origin, and the instantaneous separation between m1 and m2 is nothing but r2 minus r1, which is r. Let's write down the equations of motion. So as you can see, when the molecular system is oscillating, m1 is displaced towards the left, which is negative displacement. m2 is displaced towards the right, which is positive displacement. So for the first mass m1, I can write F is equal to ma, so minus m1 r1 double dot equal to force is the restoring force, which is minus k into the displacement r minus r0. Minus minus cancel, so you have m1 r1 double dot equal to k into r minus r0. Taking m1 to the right hand side, you have r1 double dot equal to k by m1 r minus r0. Same way you write the equation of motion for the second mass m2. Here displacement is positive, so m2 r2 double dot equal to minus k r minus r0. Taking m2 to the right hand side, you have r2 double dot equal to minus k by m2 r minus r0. So you have two equations. Now you subtract equation 1 from equation 2. So you get r2 double dot minus r1 double dot, which is nothing but r double dot equal to minus k into 1 by m1 plus 1 by m2 into r minus r0. Now the term inside this bracket, this is nothing but m1 plus m2 divided by m1 m2. When you take the inverse of that, m1 m2 divided by m1 plus m2, this is known as reduced mass of the system, mu. So I can rewrite this equation in terms of reduced mass as r double dot equal to minus k by mu r minus r0. Now you compare this with the classic harmonic oscillator equation. For a harmonic oscillator, I know the equation of motion. This is equal to x double dot equal to minus k by m x minus x naught, right? Where this particular term k by m is nothing but omega square, or the angular frequency omega equal to square root of k by m, right? So this is the frequency of oscillation. Now you can compare these two equations. On the left hand side, I have the second derivative of the instantaneous position, so that's true here. And on the right hand side, I have displacement from the equilibrium position here inside the bracket. Then I have the spring constant divided by the mass here, and here since you have two objects, you have a reduced mass here. So basically these two equations are exactly same. And in the case of harmonic oscillator, I know the frequency of oscillation ready-made, omega equal to square root of k by m. Since these two equations are exactly same, then in the case of this molecular system, I can follow the same method and write the frequency of oscillation as square root of k by mu, right? So just by approximating the molecular system to a harmonic oscillator, I can directly calculate the frequency of vibration omega equal to square root of k by mu, or in terms of potential I can write this is equal to square root of d square u by dr square at r0, which is your k multiplied by 1 by mu. So this is a very important application of the energy diagram. So this is how you theoretically calculate the vibrational frequency. You can also experimentally measure the vibrational frequency using IR, infrared spectrometer. Okay. So once you get the vibrational frequency, you can calculate the force constant from this equation. For example, if you have a molecule like HCl, you know the mass of hydrogen atom and chlorine atoms. From that you can calculate the reduced mass mu, and experimentally you have measured what is the vibrational frequency omega. So from these two you can back calculate the force constant. For example, for HCl molecule, the force constant is around 500 Newton per meter. So this is one of the important applications of the harmonic oscillator model. Now one thing you have to particularly keep in mind that the harmonic oscillator approximation works only for small amplitudes or only for small oscillation. Why? For large amplitude, you will have to include all the higher order terms. When you include all these higher order terms, then you will not be able to approximate the potential energy function to a parabolic function, because here you are going to have all these extra terms. And what is the physical implication? When the amplitude of the oscillation is small, you can approximate a bound system to a harmonic oscillator. On the other hand, if the amplitude of oscillation is sufficiently large, then the bound system no more behaves like a harmonic oscillator. It starts to behave like an anharmonic oscillator. So that's the bottom line. Now, so far in our work energy theorem, we have been considering only the conservative forces. But we know that oftentimes in physical systems, both conservative and non-conservative forces act simultaneously. For example, if you take an object falling through the air, it experiences conservative gravitational force and it also experiences the non-conservative force of friction. Right? So here both the forces are acting on the system. So let's now try to extend the work energy theorem to include non-conservative forces as well. So if you write the total force F as the conservative force Fc plus non-conservative force Fnc, then since the work energy theorem is true whether or not the forces are conservative, the total work done by F as the particle moves from initial position A to final position B is given by WBA total equal to integral A to B F dot dr. Now I can write F in terms of Fc and Fnc. So this is integral A to B Fc dot dr plus integral A to B Fnc dot dr. Now the first term is nothing but the negative of change in potential, right? Because for conservative force I can write the force integral in terms of the corresponding potential energy. So first term is nothing but minus UB plus UA. And second term is the work done by the non-conservative force, right? So let me call it as WBANC. Now from the work energy theorem, we know that the total work done in moving a particle from the initial position to the final position is nothing but the change in kinetic energy. So I can write WBA total equal to KB minus KA. Now I have two expressions for WBA total, which means I can equate them. So when I do that, I get minus UB plus UA plus WBANC equal to KB minus KA. When you rearrange the terms, you get KB plus UB minus KA plus UA equal to WBANC. And the sum of potential energy and kinetic energy is nothing but the total mechanical energy E. So I can write EB minus EA equal to WBANC. So here you can clearly see the difference between conservative force and non-conservative force. For example, if there was no non-conservative force acting on the system, then the right hand side, work done by the non-conservative force is going to be 0. So you get EB minus EA equal to 0 or EB equal to EA. So this is what we have learned in the previous classes. In the case of conservative force, the total mechanical energy of the system remains conserved, right? But that is a special case. This is the more generic case. So whenever you have both conservative and non-conservative forces acting on the system, then the total energy is no more conserved. It depends on the work done by the non-conservative force. So that's about work energy theory. Next is the general law of conservation of energy. So this is a one-page write-up in your reference book. There are no detailed mathematics involved here. You can read it as an assignment. Okay, so I'm leaving that portion to your self-study. And before winding up the discussion on work and energy, let me introduce another important parameter related to work, which is power. So power is defined as the time rate of doing work. So if a force F acts on a body which undergoes a displacement dr, then we know that the work done dw equal to F dot dr, force into displacement. And the power delivery by the force is defined as P equal to dw by dt, time rate of doing work. Okay. So let's substitute for dw here. This is F dot dr, and if you assume that the force F is a constant, then this is going to be F dot dr by dt. Dr by dt is the velocity, so this is F dot v. So power P equal to F dot v. The unit of power in SI system is watt. 1 watt is defined as 1 joule per second. And in terms of CGS unit, the unit of energy or unit of work is erg. So 1 watt is 10 to the power 7 erg per second. Another popular unit for power is horsepower. This is according to the English system, and 1 horsepower equal to 746 watt. So if you look at the history of physics, you will find that the invention of steam engine is what led to the Industrial Revolution. So prior to Industrial Revolution, people used to use horses for doing heavy mechanical work. Suppose you want to lift some object, or you want to rotate some wheels in your industrial places. For all that, people used to use horse. Then James Watt invented the steam engine, and he found that steam engine will be able to do mechanical work just like a horse does. Now he wanted to market his product. Now for marketing strategy, he thought it will make more sense to compare the work done by the heat engine with the work done by a horse. Okay. So that's how he introduced the metric of horsepower. So 1 horsepower is nothing but the amount of work done by a horse to lift a mass of 550 pound, which is approximately 250 kilogram, by a height of 1 foot in 1 second. So when you compute that, this is equal to approximately equal to 746 watt. And power rating is not only important for machines, it is also applicable to human beings, because we also do work all the time, right? And the rate of doing work you can calculate in terms of power delivery. For example, a human being in good physical condition can develop between 0.5 to 1 horsepower for 30 seconds or so, for example, while running upstairs. So this is quite a high amount of power generated. But human beings can generate high power only for a short time. For example, if somebody is working continuously for 8 hours, then all the 8 hours he cannot generate such high power. In such cases, the average power drops to approximately 0.2 horsepower, which when you convert into watt, it's around 150 watt. So once you know the average power, you can calculate the total work done. So how do you calculate the work done? You simply multiply power with the amount of time spent, right? So I have 8 hours. So 8 hours is nothing but 8 into 3600 seconds, because each hour consists of 3600 seconds. Multiply that with your power value 150, you get around 4.3 into 10 to the power 6 joule, which when you convert into calories, this is around 1000 kilocalories. And 1 kilocalorie is approximately equal to 4200 joule. So usually kilocalorie is the unit used to express energy available from food. Okay. So if a person is working for 8 hours, the amount of energy spent is around 1000 calories. In other words, he need to intake 1000 calories through his food supplements, otherwise the person will feel tired. He will not be able to do work. Okay. So in a day of 24 hours, we human beings are active for at least 15 to 16 hours, and during this time we will be doing several activities, several works, and for all that energy is spent. So when you calculate that in terms of power, that's why people say, like the dietitians say, that a normal active person requires around 2000 to 3000 kilocalorie per day. So you need to give this energy in terms of the food intake, otherwise the person will not be able to function normally. And the power values are also very important when it comes to vehicles. For example, if you take a 150cc bike like Pulsar 150cc, you will find that the power delivery is around 13.8 bhp. Now bhp is another unit of power, a more popular unit I would say, and this is known as brake horsepower, which is almost same as the horsepower. 1 bhp equal to 1.013 horsepower. On the other hand, if you take a car like a 1.2 liter engine Maruti Baleno car, its power rating is higher. This is 83 bhp. So a car engine produces more power compared to a bike engine. And if you go to a supercar like a Lamborghini, its engine is more powerful. It produces around 750 bhp. Now, why does a car require more power compared to a bike? The answer is pretty simple, because bike is much lighter compared to a car. A Pulsar 150cc bike is maybe like 140 or 150 kilogram. On the other hand, a Baleno car is around 1000 kilogram. So to move a car, you need to put in more effort. The engine has to produce more work. In other words, the engine has to generate more power. That's why a car has higher power compared to a bike. So in the case of a Lamborghini and Baleno, Lamborghini produces much more power. And power in a way is also related to the maximum speed a vehicle can achieve. So here you cannot compare a bike and a car. You need to compare two vehicles of similar class. So when you compare these two cars here, since the Lamborghini has much higher power, the maximum speed Lamborghini can achieve is much higher than a Maruti Baleno. So if you look at the tables, you will see that Lamborghini can reach maybe like 350 km per hour, whereas Baleno can reach maybe up to 150 km per hour. So this is because of the difference in power generated by the two engines here. So this is one way of looking at work done. So with that, we will come to an end of our discussion on work and energy. That also marks the end of module 2. In the next class, we will start a new discussion on angular momentum or angular motion. So stay tuned for that. Thank you.